Welcome back to the lecture series on application of nanotechnology in agriculture. So, in this section we have been talking about multifunctional nanomaterials, and we are talking about the case study of titanium dioxide. So, just recollect back. So, this is what titanium dioxide can do. If we have talked about it, the multiple application of titanium dioxide, we talked about its pollution remediation, water splitting, dye-sensitized solar cells, anti-fogging, self-cleaning. So, and we talked in depth about the mechanism of action of generation of free radicals. So, one of the challenging problems in these kind of material is the problem of recombination. What really that means is recombination of photogenerated charge carrier is a major limitation in semiconductor photocatalysis, and it reduces the overall quantum efficiency. What essentially happens is this: when you are generating these kind of species in the valence band and in the conduction band. So, this is the conduction band. So, these are happening for a very delta t period of time, some femtosecond, some exceptional small period of time. Even before something happens, these two recombine, and this is a huge problem of recombination, which is rate limiting. Okay. So, recombination of photogenerated charge carriers, recombination of photogenerated charge carrier is a big issue. It's a drawback. So let's summarize the schematic of TiO2 as photocatalytic mechanism. So, this is how it looks like. So, you have the valence band sitting here, you have the conduction band sitting here, okay, and you have the light which is falling out here with the h nu, as we talked about, less than 300 nanometer, 390 nanometer. So, here you are having the holes which are positive, deficient in electron, and you are having the electrons. Okay. And this is your conduction band, whereas this one is your valence band. Okay. So, now you have a band gap in between, which is Eg, which is your band gap. So, whenever there is an excitation, the electron which is moving, and there is this process which we have shown through individual reaction, there is an oxidation happening here. So, which is essentially, this is that photo oxidation, which dot hydroxyl radical is generated here, whereas in the conduction band there is a reduction which is happening, and that in that reduction reaction O2 plus electron making O2 dot minus, which is superoxide radical. So, this is the schematic of titanium dioxide photocatalytic mechanism, and there are series of oxidant half cell reaction which is happening, and those oxidants which are generated are OH, which is hydroxyl radical, O3, which is ozone, H2O2, hydrogen peroxide, hypochlorous acid, HClO, and chloride. And each one of them, if you see their half cell reaction, it is something like that: OH dot plus H plus electron forming water, and the oxidation potential is around 2.80 volt. So likewise, there are series of these reactions which are happening here, which are not of significance, but one of the areas where much of the work has happened in last 20 years is this. People have manipulated these molecules to reduce this band gap from, in titanium oxide, 3.2 electron volt to a lower amount, and this could be done by coupling some molecule here at the nano level. So which falls under the whole area of band gap engineering, where you are ensuring that this material generates electron at a lower energy. You do not need intense, because if you follow E is equal to H nu, right, where E is the energy and nu is the frequency. Now if you have to use high frequency, high energy, something like an UV, which is pretty high energy material, high energy intense light you have to produce. Now instead, if you could do it in visible light, which is a low energy, much more, and even if you could do it in, say, IR light, infrared, which is much more lower energy. So those are some of the engineering aspects of TiO2 molecule which has happened, where people have shown they could use the visible light for visible light active titanium dioxide photocatalysis for environmental application, and that needed a lot of those modification using different kind of materials. So people have shown that they can go all the way. I will just take this. So as of now it is 3.10 electron volt. It has been reduced now almost to 2.86 electron volt. Okay. So there are several studies which are happening in that area, but what is important is this is one of the emerging field where there is lot of application of nanomaterials, nano engineering which is happening. Exactly on the same line, I will draw your attention to the next molecule, which is FeS2, pyrite. If we look at pyrite has been used, and we have talked extensively about pyrite. Pyrite has been used in agriculture with our discoveries showing that it is a seed stimulant. It is used as root treatment. Okay. Now pyrite is one of the profound solar cell material which absorbs in the far red region. So it means this is a semiconductor. Okay. And pyrite has another application exactly like titanium dioxide. Since pyrite in the presence of water it generates H2O2. This H2O2 could be used for degradation of organic waste. You are realizing? Same molecule, almost the same geometry or the same strategy it is following. So pyrite has multiple applications. Pyrite could be used as an agricultural material. Pyrite could be used as attempts are being made to make it as a solar cell material. Pyrite could be used for organic waste, and maybe pyrite could be used for hydrogen generation. Okay. So there are multiple such applications. So what I wish to highlight, and another thing what I didn't talk to you is something called a dye-sensitized solar cell. When you talk about dye-sensitized solar cell, it is something like this. In nutshell, you understand it. Dye-sensitized solar cells are following the same logics what I told you. So, you have a photoactive material out here. This photoactive material receives light of XYZ wavelength, whatever excites its electron. It generates an electron. Okay. This electron is then put into the circuit to do the necessary work. Okay. Whereas, now this moiety, which is now devoid of electron, is being got back to its ground state by iodine molecules which are there, I2, I3, and lot of shuffling which happens, which in nature provides that infinite source of electron for nature is manganese cluster. In nature does it using manganese cluster. If you go back to the photosynthesis where I started, so nature uses manganese cluster as its electron source, that infinite electron source. Whereas out here in dye-sensitized solar cells or grid cells, you can pick up any of those reviews. It is iodine molecule which supplies that additional electron. So, coming back where I started this journey with you people, these are some of the points what I again wish to highlight. So, the future, when you talk about, I told you that cleaning of water, industrial, agricultural drinking, garbage and waste disposal, desalination of water, and what we are looking forward to is multifunctional, sustainable green material. So, if you look through the last 5 lectures what I have been given, is basically I am stressing upon multifunctional, sustainable green material having multiple applications: agriculture, energy, waste management, water purification, electronics, and other miscellaneous applications. Okay. And in that context, we have talked about two case studies and FES2. So, there are many such material which I could not cover, but they all are multifunctional. Similarly, titanium oxide, there is ZNO, zinc oxide, which is also photocatalytically could be used for breaking down of the water, purification of water. Zinc oxide is being extensively used. Yet, these are some of the properties what has to be kept in mind. They should be environmentally benign, easily degradable, and safe, acceptable, compatible with the living systems. This, along with some of the other aspect which I highlighted out here: low cost, low toxicity, good thermal and chemical stability. These properties are to be kept in mind while we talk about synthesizing any of these materials. So, future, much thrust will be on understanding the economics of the nanomaterials, their multifunctionality, their sustainability, their green manufacturing technologies. And second thing, much of these synthesis, the futuristic industries won't be the big industries, those will be small unit. So, big reactor concept will slowly kind of falls down, and it will be small reactor concept where you have multiple units, just like human body, smaller units to do the reaction. With this, I will request you to explore whenever you pick up any nanomaterial, try to see, or any material as a matter of fact, what all usage it could have other than the one which you are keen, because that will give you a very different perspective of looking at a material. The same thing could be used for multiple things. Say for example chlorophyll. Chlorophyll plant is using for as its electron donor by trapping sunlight, but then chlorophyll one day maybe could be used as a semiconductor material. It's just we have to stabilize it in artificial or synthetic settings, because it's all in the plant, much more stabilized. And another aspect what I wish to highlight here, one of my mentor once taught me, is that in nature nothing is permanent. We see leaves, they become yellow after a while, a few months, whatever. Nature makes things, nature breaks things. Nature does not learn about anything called permanency. There is nothing is permanent in nature. If something is permanent in nature, then there is a problem. You cannot degrade it. You cannot get rid of it. So whenever you make materials, whenever you think of materials, you should think one of the prime concept of sustainability is that it should not be everlasting. It should break down. It should fall apart so that it degrades and again you create. So nature, the earth, the universe, these are all reactors where trillions and zillions of reactions are happening every moment, and it is evolving. It is evolving from the world. If I look at the prebiotic soup till this date, nature is evolving. Nature used to use it as electron donor as H2S, hydrogen sulfide. Today nature has evolved to water as its electron donor. I do not know where the future goes. Maybe in Mars somewhere we will see there may be another electron donor. Nature is continuously evolving. You just have to try to get the chord of nature, how nature is performing its reaction, how nature is making a difference, a huge difference in our life. And the more we learn about it, the more we will be able to appreciate two concepts which I highlight. One, nothing is permanent. Nothing ever should be permanent except change. So any material you make, if it cannot be destroyed, if it cannot be got rid of, then there are issues with such materials. And you should have a finite life, should get degraded, new materials will come. And that is where much of the sustainability issues of future will be. Green synthesis, getting materials, have a shelf life, they get rid of, and they again become elements, and again you recombine them. And much of the synthesis should be at a low temperature, because that's where you cut down on the cost, and they should be reducible. The electronics, if you look at it, started with silicon, now started with sulfides, moved to silicon, crystalline silicon, as I talked about Bardeen, Britton and Shockley, and then moving towards carbon, and maybe carbon and sulfides again. So we as a race are slowly realizing that multifunctionality, sustainability and non-permanency are the key to our progress. Thank you.